All right, so we're now going to look at the last geometric shape for change in boundary conditions with transient conduction. And so we're looking at convective boundary conditions where we're changing them. And this, we're going to look at a sphere in this segment. Okay, so geometry of the sphere. We have R naught, which is the outer radius, and then we're interested in what is going on at some radial location R. And we'll begin just like we did for the slab and the infinite cylinder. We'll begin with the approximate solutions. And we begin with the center line temperature. So here we're evaluating theta naught star, which is theta naught divided by theta I, and those are defined as being the center line temperature minus the free stream convective environment, and then Ti, our initial temperature, minus the free stream convective environment temperature. And just like for the slab and for the infinite cylinder, we have the expression C1 exp minus zeta 1 squared, and then we have the Fourier number, alpha, the thermal diffusivity times the time divided by the outer radius of our sphere squared. Bio number, we need the bio number, and that is H R naught, that's your convective environment, convective heat transfer coefficient. R naught is the outer radius divided by the thermal conductivity of the solid. And the reason why you need bio is because C1 and zeta come from tables, and those tables are functions of the bio number. So you would look those up. You compute your bio number first, and then you look them up. So that is our centerline temperature function. Spatial distribution. We have a function for the spatial temperature. And this one's a little simpler. I guess you could say it doesn't involve Bessel functions like we saw for the cylinder. However, in order to solve it, you do need to know what happens at the center line, which we have in the theta naught star term. And so here we have a trig function. Remember to be careful. That needs to be evaluated in radians. And R star, just like we saw for the cylinder, that is basically just the radius non-dimensionalized by the outer radius. So that's how we get the spatial temperature. You solve, first of all, for that using the centerline temperature, and then you, using the values that you looked at for the bio number and for the spatial location, you calculate R star, and it's pretty straightforward. And remember, what we're after here is to get that, because that gives us temperature at a given spatial location at a specific time. And then finally, heat loss. How do you calculate heat loss from this sphere? So you get that. That's a little bit more complex than we've seen for the slab and the cylinder. And then Q naught, that is just like we had for all the other ones. Total amount of energy, assuming that your sphere goes all the way to T infinity with time. So that is heat loss, spatial temperature, centerline temperature. Just like before, we also have the Heisler charts that we can use, and so that's the graphical solution. Starting with the centerline temperature, we have this plotted as a function of the Fourier number. That's going to be theta naught divided by theta I. And here we're going to have these curves, and they are functions of 1 over the bio number. Spatial distribution, you have to determine what goes on at the center line first before you can get to this one, because you'll notice theta naught is in there, and that's what you're getting. So this theta naught that you determine here goes there. That's what's going on. And this is as a function of 1 over the bio number, and we have a number of different curves that change depending upon the radial location that we're interested in, and so that would be R over R naught. That's our R star value. And then finally, heat loss, we have curves for that, and those are going to be Q over Q naught. Fourier bio squared, the bio number, and then we have this here, and that's a function of the bio number increasing in that direction. So those are the Heisler charts. We will be looking at those in the next lecture because we work an example problem. We won't look at the heat loss one, but we'll look at the central line and the spatial Heisler charts. So anyways, those are the different techniques for calculating transient heat conduction in an infinite slab, in an infinite cylinder, and in a sphere when you change the external convective heat transfer boundary conditions. So in the next lecture, we'll go on and we're going to use one example, but we're going to work it twice. Once we'll use the approximate solution, and then in the second segment, we'll use the Heisler charts and we'll compare them and see how well they compare to one another. So that is where we're going with